we can talk about 6 plus 2 cycloaddition. Will it be possible? Or if it's not possible, how are we going to make it work? So to do that, you have to be able to get the molecular orbitals, and then trying to see whether there's symmetry allowed or forbidden. So let me just go through the process that you need to do these type of reactions. So it says 3 double bonds. It's a hexatriene with 2 p orbitals, just a double bonds. Probably it will have electron withdrawing group, but the drawing says I didn't draw that. We can expect that similar types of reaction, high electrons of the double bonds, going to make a sigma bond between these 2 molecules. Then these double bonds move inside, and that double bonds move to another side, and then that double bonds will come out and make a sigma bonds to finish to close the loop, the ring. This is a cycloaddition. There's a more high electrons are in room, so it's going to make a bigger size of ring. Actually, the 8-member ring that's going to be produced. The question is, will it be possible? Will it happen like the green react? I mean, the deals of the reactions. So to do that, what we need to do, we have to look at the HOMO, highest occupied molecular orbital of these conjugated double bonds, and then the LUMO of the other components. And then we need to see whether the symmetries are matched or not. So we need to draw the molecular orbital on both sides. So let's start with the hexatriene. So since we're mixing 6 p orbitals, because there's 6 carbons and 6 p orbitals, we are going to produce 6 high molecular orbital, right? That's basically what we're going to do. Actually, we did this already before, but I'm going to remind you again. And I draw it this way because these 2 N has to be make a ring together. So I didn't draw in a linear fashion. I drew in like the C shapes. So basically, I just drew all 6 of them first, and then it's going to be pi 1, 2, 3, 4, 5, 6, and then we need to draw the molecular orbitals, talking about the phases. What phase is going to be on the same side, and which one is going to be outer phases. So pi 1, that's the one that has the all the same phases on the same side. So we expect that it's fully localized from the C1 to the C6. So that's the pi 1 we can expect. How the pi 2 is going to look like, it's going to have a node, just the one node. The best place that one node in the structure is definitely right in the middle. So 3 of the p orbitals going to be in phases, and then the other 3 is going to be out of phase. So that's going to be pi 2. Pi 3 will have 2 nodes. So every 2 organs, we're going to have the nodes placed like this. So 2 in phases, 2 go out of phases, and 2 is going to be in phases. And pi 4, we keep with the 3 nodes going down this way. And then pi 5, that's going to be 4 nodes. And then pi 6, that's going to be 5 nodes. Basically, every bond you're going to have a node. So all the p orbitals are going to be out of phases to each columns. So those are the molecular orbitals we can create with the 3 double bonds. And then, because we are mixing 6 p orbital, the number of the electrons that we're going to populate them are 6 electrons. So we're going to completely fill out pi 1, 2, 3. So these are the bonding molecular orbital. Pi 4, 5, 6 is going to be empty, and that's going to be anti-bonding molecular orbital. And then this is where you need to consider which one is a HOMO, right? Highest occupied molecular orbital is not pi 4 because it's an empty. It's not pi 1, that's because lowest energy molecular orbitals. HOMO, highest occupied molecular orbital, is a pi 3. So we're going to talk about the symmetry using these orbitals. So we did one part. Part 2 is finding out the LUMO of the double bonds. And a double bond just have a 2 p orbital, so it's going to be just a 2 molecular orbital. These should be really familiar to you. Pi 1, pi 2. Pi 1 is going to be 2 p orbitals in phases, so they're going to make a bond, double bonds. And then pi 2 is going to have a node in between. Pi 1 is fully occupied, pi 2 is an empty, it's anti-bonding molecular orbital. And which one is the lowest unoccupied molecular orbital is going to be pi 2. That's just one empty one, but that's going to be the LUMO. So now the differential molecular orbital theory is basically talking about the HOMO of the conjugate side and then the LUMO of the other side. And then we're going to see whether they're going to match the phases or not when we're interacting together. So which one we're talking about is low. I mean, we are using the one in the downside, but we can use the one in the top side too. It's based on arbitrary choices because the molecule can approach from the bottom or it can approach from the top. It really doesn't matter. But if you decide to use the lower lobe and then to the top lobe from the other side, the one side you're gonna have two p orbitals in phases, so we can say that that one is good for the bonding. But if you look at the other one, this one to that one is going to be the anti-bonding. I hope you don't make a mistake by comparing the lower one to top one, the other one, and then you just switch the top one to the top one. That doesn't work because you cannot cross the molecule that way. It has to be on the same side. So that's why this is in phase, but the other is going to be out of phases. So this is something we say symmetry forbidden. So what the symmetry forbidden is, this thing is not going to work. They're not going to cyclize by mixing these two together. So does it mean that you will not be able to do these reactions? No, there's a way to make it happen. And that is something we're going to say the photochemical reaction. The photochemical reaction is that you shine the UV light, and then what the UV light does, you make one of the electrons in the highest occupied molecular orbital to jump up. So that's why you shine the light to provide an energy. So one of the electrons is going to move up to the pi 4, which was an empty in the beginning, but after you shine the light, that is going to have just a single electron moved up. So pi 4 now becomes new, the highest occupied molecular orbital. We call excited highest occupied molecular orbital because singly occupied molecular orbital. There's many names, but you can see that the highest occupied molecular orbital now is going to be pi 4. So now we have a new the HOMO from the triene side. LUMO still stay the same. So now we need to talk about symmetry between these two. Not between the pi 3 to pi 1, but this pi 4 to pi 2. You can see that one side, we have two lobes in phases, so they're going to be good for the bonding. On the other side, now it's different. Now you got two lobes in the same phases also. So both sides is good for the bonding. So we call this thing symmetry allowed, and then the reaction will occur. So in case you want to do 6 plus 2 cycloaddition, then just heating it up is not going to make it work. You can heat up to 400 degrees, 500 degrees, 600 degrees, it's not going to be efficient. It's not going to work. But once you shine the light, even at the room temperature, this will go. But that is what this molecular orbital theory is talking about. So that basically is something that I've had asked you to do it at home. I don't know how many of you have done it, but now you say that this is something that you could do any number of the conjugated pi system. Because the other is more popular, but you can do also different sides of being created from this reaction. Continuing is further. Let's talk about 6 plus 4. As I said, 6 is a hexatriene, and we just did it, so I'm not going to change that. You already seen it, so I'm not going to do it again. On the other side, it's 6 plus 4, so we're going to have a butadiene comes in as a diene oxide. This will create the ring bigger than what we made before. 6 plus 4 makes it 10. It's a 10-member ring. And then double bonds moving around. So these double bonds move in the middle, right? You can see that one. That double bond comes out, make a single bond, and these double bond move inside, that one move inside, that one comes out, make a single bond. So you have a place of the double bonds in the tandem ring in a particular way because of these pericyclic reactions. So the question is, will this work? If it's going to work, do you do it thermally or do you do it photochemically? So that is what we're going to check one more time. And since we have done this part already, it makes it simple. We need to do the molecular orbitals of the butadiene, which you probably have seen already. So this shouldn't be too difficult. So we got 4 p orbital mixed together. So we're going to create 4 molecular orbital from the butadiene side, pi 1 through 4. And definitely pi 1 is going to be same phases all the way from the 1 carbon to the carbon number 4. So that's going to be pi 1. Pi 2 will have a 1 node that is definitely placed right in the middle. 2 in the same phases, 2 go down phases. Pi 3, 2 nodes. So out of phases, in phase, out of phases. And then the pi 4, basically all the p orbitals going to be out of phase. And then you know that pi 1 and 2 are going to be completely occupied because we have a 4 electron to fill in. And then the 2 on the top is going to be empty. Which one is going to be the LUMO? Not pi 2, it is pi 3 because that's an empty orbital, right? Double bond, that was a pi 2. There's only 2 orbitals there and that was empty. But in the case of butadiene, you got pi 3 empty, that's the LUMO. So now we are checking the symmetry. Pi 3 of the hexatriene, that's a HOMO. And then the pi 3 of the butadiene, that's a LUMO. And then see whether the symmetries are allowed or forbidden. So when we're connecting them from the one side, the downside and top side, you see that they're in phases, which is good for the bonding. If you check the other side, this is basically also good for the bonding. So what that means is 6 plus 4 cycloaddition reaction is symmetry allowed. You can do this reaction by just simply heating it up. And we can talk about photochemical reactions. And you can probably expect it's going to be symmetry forbidden. But let's do that again. Same thing. If you shine the light, then what happened was this HOMO, electrons in the HOMO is going to jump up. So pi 3 is not going to be the HOMO. Pi 4 is going to be the excited HOMO for this hexatriene. And we are checking the symmetry between this singly occupied molecular orbital with a LUMO on the other side. You can see that that side is in phase, but this one versus that one, that is going to be out of phase. So clearly symmetry forbidden, and then the photochemical reactions of the 6 plus 4 cycloaddition will not work. So I hope that this gives you an idea that how these frontier orbital theories are used to predict a particular cycloaddition reaction. It can be used like 2 plus 2, 4 plus 2, 6 plus 2, 8 plus 2, all sorts of different numbers, because this is what the conjugate system does for the reactions. So this is something that I want to talk about before we move on.